Hello everyone, welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. And one of my tasks before I introduce our guest speaker is to collect some data from a couple poll questions that will help both focus the presentation and ensure that we're kind of targeting the right audience. So if you would please, obviously there's no obligation or liability. So if you would please kind of help us with some feedback. The first question is, have you or anyone that you've worked with been involved in an arc flash event? Now, obviously, this is a sensitive subject, and it's always eye-opening how frequently people respond in the positive. So let's give this another 20 seconds. Again, there's no liability. We will be issuing attendance certificates for the time that folks have attended, and they will be sent out if you complete the survey at the end of the presentation. So make sure everyone completes your survey. All right, looks like we have a quorum. Here's how folks have weighed in. And again, I'm always just surprised how much this has affected people in their workplace. All right, so the next question is, where do you stand with respect to arc flash compliance at this point? Again, strictly feedback for informational purposes, no obligation or liability. But it gives us a perspective on kind of what your understanding or awareness of some of the standards involved may be. And we do appreciate your attendance today. It looks like we're about halfway to a quorum. Let's give this another 15 seconds. Looks good. Here's how folks have weighed in on this one. And it's kind of a 50-50 split. All right. And then finally, when was your last arc flash assessment completed or updated, if you haven't, if you have had one done? This helps our presenter kind of align his wheels as he's going through the material. All right. Thank you again for attending today. Here's how folks have weighed in on this. Excellent. Now I'd like to hand the baton over to Mr. Lee Marshasalt with Workplace Safety Solutions. And give me just a second. Okay, Lee, you have the baton.
So, all right, thanks, Jim. So again, I'm Lee, and I've been doing this now for 44 years. This month is when I started, actually, years ago. Started at a power plant. I grew up building houses when I was a kid with my father, and started at a power plant when I graduated high school. And it was commissioned in 1905. So this equipment was built in 1880, and it's still running today. And so it was a great way for me to learn and to get an experience of what electricity is all about. And I've been learning every day since, and so I love working with electricity and always have. Um, I stayed with the power company for about 25 years, and after I was a safety manager, I left and started this business. And so I do this. We do arc flash studies, electrical training, and I do expert witness work and things like that. So I do a lot of investigations for incidences, and so that's kind of my background. So I'm going to go through the program. What we're going to talk about today. First off, we're going to talk about the effects of arc flash incident. I'm not going to spend too much time on some of this stuff, like I would on training new people or something, but I do want to touch base on what the hazard is. We'll talk about the importance of conducting an engineering study, and we're going to talk about the labels versus the tables. Labels meaning the electrical engineering study labels, or tables going to NFPA 70E tables versus the engineering study. We will talk about maintenance and important, including short circuit and coordination studies on a regular basis. So that's an important thing that a lot of people kind of miss. They do a short circuit and coordination study when they develop and install the new switchgear or new panels and things like that. But then it's sort of like, all right, install it, set it, forget it, and kind of thing. And they don't seem to repeat the short circuit study and the coordination study. So we're going to talk about that and how that ties into the arc flash analysis as well. And then we'll talk about potential consequences, including civil litigation and some case studies that we'll talk about. And then we'll describe some ways to mitigate the arc flash hazards, which those of you that have done the studies probably have done that. As far as reference standards, so we have the National Electric Code. It's kind of like the mother of all electrical codes. And that started in 1897 when they started having fires with the electrical systems that they were installing in New York City and Philadelphia and stuff. So there was about 6 or 7 different standards back then, and they all got together. These committees got together and decided on one, which was the National Electrical Safety Code from the National Fire Protection Association. So that's NFPA 70. That's the National Electric Code. From that, we got 70E. In 1975, OSHA contacted NFPA because they wanted to develop an electrical standard. And they still didn't have one. So NFPA came up with the electrical safe work practices in 1976, and that they called it 70E. So it's like an arm. It's information that came from the National Electric Code, and it's kind of been built up every year since. It used to be every 4 years they would update it. Now it's every 3 years, and so it's much more comprehensive than OSHA, because OSHA took the 1980 70E and used that for the standards and the safe work practice standards regulations, and that's still in effect today. So they're looking at changing that and updating that, so hopefully that'll happen soon. 70B is a great document as well. It's a maintenance guide, and it gives you some ideas on what to do for maintenance. And a lot of civil litigations are just basically due to lack of maintenance, that whether it's damage or injuries or fatalities. So OSHA, there's 269, there's subpart S, subpart K, there's subpart V, there's 1910-137. They're all electrical regulations now, so we can follow those, but they all come from the standards. National Electric Safety Code is more of a utility or utility-like work standard for medium voltage. And then there's the IEEE 1584 standard, which is used for arc flash analysis. That was updated in 2018. So that was why we asked the question about if you've done the arc flash study in the last 3 years, because the new standard came out in 2018 and actually was available, I think, 2019. So that changed things. It went from 6 formulas to 66 formulas, and so it's a lot more comprehensive than it was. It does require more data to be collected on the type of switchgear you have and so forth, but it's a really good way to go. But you want to probably update that when you can. Don't go more than the 5 years if you had it in 2016 or 17. Well, that would be 5 years if it was 2017 now anyways. So that will change things a little bit. NFPA 70 says we have to do a job safety plan, and with that plan we have to do a job briefing, which requires us to assess hazards, and then there's an expansion of that in NFPA to not just assess hazards but also the risk levels associated with those hazards. So we'll talk about that a little bit. So the big thing with the safety plan and assessing the hazards, that gets into the tables and the labels from an arc flash standpoint. Shock is what it is. We have to know what we have to do for rubber gloves and all those kinds of things. But for arc flash, it's a little more vague, especially if an arc flash analysis has not been done. The other things that I see that people or companies do is they will have an arc flash study done, and we may find some breakers or some equipment that's over dutied. It's not rated for the fault current anymore, and that's a pretty serious situation that can impact what the arc flash level is. Um, so they think that, well, they'll put the stickers on that we provide and so forth, and and they're done. But in reality, that's not really the case, because they probably should be replacing their equipment that is not rated for the fault current. So it's a liability thing that people need to be aware of, that once it's in writing and it says you've got this issue and you don't address the issue, but it's still in writing, that's something to consider as you go forward. So what is an arc flash? So an arc flash is a ball of fire that comes out of equipment based on a fault, from a ground fault or a short circuit, and I'll talk about the differences in that. And it's got a lot of heat and energy to it. So they call this incident energy. There's a heat component, there's a pressure component, and it depends on several things, which I'll talk about in a second. But the big thing is it's 35,000 degrees. That's hotter than the surface of the sun. It will melt hardened steel instantaneously, just like that. And if it melts hardened steel that easily, if you get your face in the way and you're not protected, just think of what it does to your face. So that's one part of it. The box effect is about 10 times greater in a box like this, like you're seeing in the panels and things like that, than it would be in open air. So you don't see linemen with full suits on because it's 10 times less than it is. Plus the fault current is going to probably be less on the primary side of things than it is on the secondary side. So there's a few reasons, but OSHA does not require suit hoods and full suits for open air work. So the severity depends on the arc to have enough energy to cause a thermal burn of greater than 1.2 calories per square centimeter. So for those of you that are new to this, calories per square centimeter is the measure of the incident energy level that you have. So when you think of calories, you think of running or eating calories and that kind of thing. It is a measure of energy. This incident energy, as I mentioned, has the two components, a heat component and a pressure component. So 1.2 is the demarcation between a first degree burn and a second degree burn. That's an important number to know, because that's what our arc flash boundary is. Once you go inside that boundary and go over 1.2 calories per square centimeter, you need to have a shield and a arc rated clothing at a minimum. And then you have to calculate what it is at your working distance, where you're actually going to work, and when you're actually closer to that arc flash. Then you need to calculate that so you can gear up your PPE to that level. So 1.2 calories, just to give you an idea of what heat it is, that if you have a 1.1 calorie arc flash, and it goes bang, you're going to have like a sunburn on your face and on your hands. If it's a 1.3, bang, now you've got blisters. So we don't want to go there. So we want to protect our employees to make sure that they don't get that level of arc flash. So that's an important number. Copper vapors expand 67,000 times. Now we're going to talk about the pressure. Molten metal travels out at 700 miles an hour. So even though our arc flash boundary may be here, doesn't mean the molten metal stops. It still keeps going. So you may do a risk assessment and say, I'm going to put a shield on anyway. Pressure waves. So pressure waves can be 2,100 pounds per square inch. That's why you have all this molten metal. And sound waves, 140 decibels. When I was a young electrician, I was working in a substation in Burlington, Vermont in 1992. And I closed in a fuse with a dead short, and the bang was so loud that I couldn't hear for 3 hours. At that time, we were not required to wear hearing protection like it is now. And I have hearing loss and tinnitus from that event in 1992. And that was a long time ago. I was a young man. So anyways, that's something to think about. Intense light, of course, that's why we have shields and tinted shields that will help prevent retina damage. They are now making hooded shields that actually will darken up automatically, like the welding shields, and so that's now being done. So it's measured in calories per square centimeter. The level depends on several things. First off, what is the bolted fault current? So the bolted fault current is everything that's available from the system, and it may be up to 200,000 amps on a 480 volt system. So if you have 200,000 amps, that's a lot of available fault current, and it's going to contribute to a large scale arc flash event. It can. So then the other thing is clearing time. So a breaker and a fuse has a certain amount of time that it will trip or it will open up. All breakers, all fuses, relays, every protective device has a time current curve, certain amount of time and a certain amount of current. And that will trip in this bandwidth that has a certain amount of time and a certain amount of current. And everyone has their own specific time current curve. And so when you're talking about this incident energy level, the incident energy is directly proportional to clearing time. Directly proportional to clearing time. That's pretty important because if I'm working downstream from a fuse, I know that a fuse can operate really quickly. It will open up in as little as a quarter of a cycle. Remember, we have 60 cycles per second. So a quarter of one cycle is a very small amount of time. And so if that opens up when there's a fault, it opens up so quickly that the ball of fire just might be a little ball of fire that's 3 or 4 inches around. And if I'm working downstream from a breaker and the breaker is 3 cycles, now this was a quarter of a cycle. Now I'm going to go to 3 cycles and it's going to keep on going and going, and now I'm totally engulfed in a ball of fire because it's a breaker that I'm working downstream from versus the fuse. So what I'm working downstream from has a big impact on it. And so those two things are the key parts of what needs to be collected, along with wire size and type and length and all that. But the clearing time and the fault current are some really key components of why or how big this arc flash is going to be. But the key to remember is the clearing time is directly proportional to the incident energy level. So what causes it? So it's either going to be a ground fault, and usually most of them start off with a ground fault. What can happen on 480 volts and higher is the air can become ionized. So that means there's enough voltage with 277 volt system to cause electrons to flow through the atoms in the air, and that creates a plasma, and that plasma turns to a three-phase fault, and then it blows into this big ball of fire. So that can't happen when you have a fault that's a single phase. A short circuit is going to be phase to phase. The same thing will happen. It'll go to a three-phase fault. If this were to happen on the single phase, were to happen on the low side, it probably would not ionize to a three-phase fault because the fuses would be fast enough to isolate it to that one single phase. Maybe, not always, but maybe, depending on the type of fuses you have. But up on this part, you're a distance away from a breaker probably, so it's definitely going to be enough time to cause this to go. I mean, I say definitely. It could be a fast-acting breaker, but it very likely would be a three-phase fault. So before we open this up, it's considered guarded. So when these are guarded, the screws are all in place, the latches are closed, everything's in good shape. This is not guarded. This is a door. This is what happens sometimes with motor control centers. They'll close the door and turn it on, and then there's a little interlock so it stays closed, but it's not all the way closed, and that's not considered guarded. So you have to take the screws and twist them to engage the screws to make sure that it's guarded. So you'd have to have PPE to work around this stuff if it's unguarded. But if it's all guarded, then you're okay. There's no PPE that you have to use.
Lee, Lee, let me
Yes.
interrupt you. So we have a question here about this. Don is asking, what is the clearing time difference between breakers and fuses? If you do not have breakers, how much more at risk or less risk are you with fuses?
Great question. So fuses are always going to be not, I mean, you can get fast acting breakers and slow acting fuses, time delay fuses. So it all depends on the time element and the time current curve of what it is you're doing. Fuses, the good thing about fuses is they don't require maintenance. Breakers require maintenance. And so if they're not maintained properly, that could delay their operation and it wouldn't be operating within the time current curve. A fuse doesn't require maintenance, so it's always going to open up the way it's supposed to according to the time current curve. So that's a good thing. And generally, if you look at the notes section of the tables in NFPA, it gives you a little idea of what generally the trip time is for various breakers and fuses. So a fuse it'll say a fuse is from a half a cycle to 2 cycles. And in reality, you can get even tenths of a cycle with some of these new electronic fuses. So it's very quick and very fast acting. Breakers may be 1.5 cycles for molded case breakers, and you could go all the way up to 30 cycles for time delay breakers for motor controls or VFDs and things like that. So where you have 30 cycles, that's like it's a total engulfment of your body into this arc flash. So you can get some really high arc flash levels. Hopefully that answered your question.
Yeah, and so there's a follow-on from Chuck.
Okay.
Will you be talking about the Z impedance fault where you have listed on fault current, where the Z impedance
Uh,
value comes from?
yeah, actually the impedance is, let me go back here. So this is actually one of the things that was on here, and maybe that's why it was brought up because did list impedance and distance. Distance is your friend when it comes to arc flash. The further out you are, the more significant the drop is. So one example, we had an arc flash level of 101 calories. 3 feet out from that, it dropped to 35. So that's a really good thing to think about. The impedance. So impedance is like the electronic version of resistance, electrical version of resistance. It's based on inductance and capacitance, and I don't want to get too much into this because some people are more safety related than they are electrical. But if you have inductance or capacitance, that will have an impact or impede the current from flowing through that conductor, just like resistance. And so the higher the impedance, it's going to drop the fault current, but it's going to increase the clearing time. So you could have a 300-foot run of wire and have a certain calorie rating at this breaker, and 300 feet away feeding a disconnect, it's actually going to be higher because the clearing time is going to change. The fault current's going down, but the clearing time is going up. So it's going to allow this arc flash to go out a little further. So that's something that has to be considered when you're doing a study of that, and that's why you consider the wire types and lengths and all that. But also motor load has a factor on that. So if you've got 50 horsepower motors and larger, that can also cause more inductance, and that's going to cause more overall impedance, and that's going to bring down your fault current and bring up your clearing time as well. So that does have an impact on there. Okay, and it's all part of the study. We did this. So we need to know what our arc flash hazard is at 18 inches, and we need to know what our arc flash boundary is so we can keep non-qualified people safe by barricading at that level. So that's the barricade. That's the 1.2 calories area. Up here, it's going to be much higher, and we just need to make sure we gear up for that level before we open up any cabinets. Another form of impedance is the transformer. So this is a transformer nameplate, and impedance is on the transformer itself. So the 480 volt secondary, it's a 1500 kVA. Did some calculations down here, so we've got 1800 amps of load potential from this transformer. And if you calculate out the kVA rating of this particular the bolted fault current rating is 32,000 amps roughly. So if older transformers will have a lower impedance, and if you have a lower impedance, you're going to have more fault current. And so this gives you an idea of a 2% impedance with an older transformer would be 90,000 amps of fault current. So that's going to have a pretty big impact on what your what your levels are as you go and you do your study. Another thing to think about too, if you're working downstream from a transformer and you're protected by something on the other side of the transformer, so you're working on 208 volt stuff and there's no 208 volt disconnect after the transformer, there's only the 480 volt disconnect on the primary side of it. So you now, whatever happens to you, the short circuit that occurs at the 208 side has to be protected by the fuse on the 480 volt side, and it's really hard to see that through that impedance of the transformer. And what happens usually is it'll burn itself clear and before the fuse actually blows or the breaker trips. So that is an impact from an impedance level of what the arc flash hazard can be as well. So it's again part of your assessment. Okay, so we need to know what this arc flash level is at our working distance, and that's always going to be 18 inches for low voltage. It'll be 3 feet for medium voltage over 1,000 volt stuff, and then our arc flash boundary. So we talked about the clearing time. So here's the table that's an NFPA that gives you some idea of clearing time. So current limiting fuses, a half of a cycle. Molded case breaker 1.5 goes all the way up to 30 in the table. This is the section in OSHA that says that you need to do a coordination and short circuit study in so many words. But a lot of people don't realize that it's even part of OSHA. So 1910 303B5 says if you look at B4 and B5, you're going to be it'll tell you that you have to know the impedance of the system. You have to know the fault current, and you have to coordinate the system. So here's a bunch of time current curves. So these are, let's just say this one goes to the main breaker feeding the facility. And that main breaker feeds the main distribution panel. And that main distribution panel has all the infrastructure on it. So all the breaker panels, all the motor control centers, all the bus ducts, all the chillers, everything is on there, transfer switches, whatever it is. So that's what this is. So this breaker feeds the main distribution panel. The breaker then there's a breaker in that panel that feeds a 480 volt panel, and that's a main breaker for that panel. And then this is a breaker in the panel that feeds a motor. The motor goes bad and is overloaded for whatever reason, and so it trips the breaker as it's supposed to because that's the closest one to it, time-wise. Then if that doesn't trip for whatever reason, then you've got the main breaker. And so this is all coordinated. And that's good for 20 or 30 seconds. That's how much it would take for that particular overload to occur. So if you have a 50 amp breaker and you're drawing 55 amps, it may take 20 or 30 seconds to trip. But the right breaker is going to trip. So, but let's go down here. This is now the instantaneous zone. This is a very, very fast acting for ground faults and short circuits. And so if that was a ground fault that occurred, so a wire now makes contact with the case and the case shorts out, now the first one that goes is the orange one. That's now the one that is feeding the main distribution. It's coming from main distribution. So this feeds the whole 480 volt panel and 3 other 480 volt panels. So now the motor that should take out this breaker takes out 4 separate 480 volt panels. And what if one of those panels had the combustible dust for the exhaust fan for the combustible dust area? So now you've just caused and I say you, it'd be the company that owns this, has caused a combustible dust explosion risk because of not being coordinated. So this is an important thing to do, is make sure things are coordinated and that things are short-circuited. Now here's a breaker. I've got breakers like this breaker. I don't know if you can see me or not, but I've got a breaker that's 10,000 amp rated. It's a Home Depot style breaker. That's the highest rating you're going to get, is 10,000 amps, because your homes are not going to typically exceed 10,000 amps. This breaker that you see is got at 240 volts. It's good for 200,000 amps, At 480, it's good for 100,000 amps. These breakers you don't get at Home Depot. You have to go to an electrical supply store. So a lot of maintenance people that I've seen, and as we're doing studies and stuff, we see panels that were added on, small sub panels for test areas and different kinds of things. And they go to Home Depot and get a main breaker and some panels, and then it all looks honky-dory. It all works, powered up, everything's good, looks great, but it's going to blow up if there's a fault, and it's not going to operate the breaker within the time current curve. So that means the arc flash level can be much higher than what is calculated, even if you did do a study. So this coordination and short circuit study is very important, and this is part of doing an arc flash analysis. To do the arc flash analysis, you've got to collect the same data that you would do for a short circuit and a coordination study. That's why in your arc flash studies, it will tell you if your coordination is good, if your short circuit, if everything is rated for the short circuit fault current, and that's important to read that portion of the study as well to make sure that you understand. So look at the recommendations from the engineer that does the study. So this is an important part of it.
Lee, let me interrupt you just a quick.
Yeah, sure.
This question's about the unit of measure for instant energy. It's from Ali.
Yep.
He's asking, the unit of measure is calorie per square centimeter. Does that mean that square centimeter is the area of the conductors involved?
No. So it's like the so if I'm wearing a shirt that's 8.4 calorie shirt, that means it's good for 8.4 calories in every square centimeter of that shirt. So that's how much incident energy it can handle in that small little space. So that's how they measure it with over an area with that incident energy. So good question. Okay, here's a study that was done. This is an interesting study. So this company bought a facility that was an older facility because they grew out of their older facility, the one that they had. This facility that they had was installed in 1962. They had 4,000 amp switchgear and a bunch of 480 volt panels and all kinds of stuff through the facility. That was 1962. So they decided they're going to replace it, and they didn't need to have 4,000 amps for their particular loads. So they put in a 1,500 amp switchgear like you're looking at right here, and then they replaced all the infrastructure inside with new electrical equipment as well. So we go in to do the study, and they're thinking they're doing well, but the arc flash boundary is 115 inches, and it's 76 calories per square centimeter. And they're like, why is it so high? Well, the reason why it's so high is because it's still got the same transformer outside that fed the 4,000 amp switchgear. So it's like a 5 MVA transformer, large transformer, and it's got low impedance because it's a 1962 vintage transformer, probably older than that. So that caused an immense amount of fault current available and brought up the arc flash level very high. So the arc flash level is extremely high on this switchgear that's brand new, and it's dropped after the main. This is the main distribution panel, so all the infrastructure is fed off of all these breakers and so forth. And it's lower here, but you have to protect yourself for the worst case because it's all connected together. And the worst case is 176 calories, so the suit is not enough. You can't do anything with this switchgear without shutting it down by the utility outside. So what they did was they asked the utility to replace the transformer, of course at a cost, and they replaced it with a 1500 kVA transformer, and it brought it down to 28 calories from where it was. So that was a big change in the available fault current and so forth. Okay, and then so what it is now is what it is. So that's what they're dealing with. 55 inches arc flash boundary on the panel, 7.6 calories. So they're going to wear a shield and a balaclava. Downstream from the breaker there, we're going to a disconnect switch. We're down to 2.2 calories, still over 1.2. So we're going to wear a shield and arc-rated clothing. Rubber gloves with leather protectors, by the way, are now also not just shock protection, but also arc flash protection. So now we're down to 0.5 calories. Now the thing to remember on this one, so this is a depiction of what actually happened to this gentleman. One of his probes went past the screw and made contact with the case, and there was an arc flash event. It's only 0.5 calories per square centimeter, less than 1.2. But you have to remember, this is at 18 inches. So this is the protection level. You don't need any specific protection level at 18 inches if you've got only 0.5 calories. You don't need a shield. You don't need arc-rated clothing. But at his hands, he got second-degree burns because it's at 2 inches, much higher arc flash level. In reality, this is 120 volts, and you can touch these things. So rubber gloves were required anyways. You're not avoiding contact because you can touch them. And rubber gloves with leather protectors would have protected him from the arc flash as well as the shock. So that's what the study kind of looks like. Usually 3 levels down, 1, 2, 3 is down to now this is a higher level at the main, but downstream from the main, these levels are usually at a low level, usually 3 levels down generally. This is just arc flash burn. So first degree burn is like a sunburn, it's redness. Second degree burns, you have blisters. Third degree burns are full thickness burns. You don't want to go there. That has to be usually skin grafts. So this is PP. This is showing how rubber gloves with the leather protectors hold up. Outside, these have to be longer than the leather, so that's, you can see how much damage to the rubber in themselves. They're not going to provide protection. This is not from the outside. This is from the inside. This is what ionization does in an arc flash. So it'll heat metal just like throwing keys in a microwave oven. That was a ring that this was on this gentleman's finger. This guy Mark almost had to lose his finger from the burn that he had on his finger from that burning from the inside out. The clothing that he had in this particular case was a little not quite rated for the fault current or the calorie rating, and so it breached a little bit, but it, for the most part, protected him. So qualified people generally need to know what their shock boundaries are, restricted and limited approach, but need to know that arc flash boundaries. So they got to figure out by using labels or tables of what that arc flash boundary is. And it's always a good idea for qualified people to look at the report and understand what's on the report and what the issues are that have occurred, and if there are over-duty breakers, things like that, other risky situations. We also have to barricade, so we have to know what that arc flash boundary is before we can throw that barricade out there. Now this barricade is out there quite a distance, so I would not say that this was out there for any arc flash boundary distance. This is a control cabinet with probably quite low level stuff. So the shield may or may not be needed. It may be just part of their policy that they do and use it all the time. So the electrical program in the NFPA standard says we should implement and document overall electrical safety program. Shall consider conditions of maintenance. This was added in 2015, I think. And that's important. We're realizing how important it is. Arc flash levels are not leveling off. As a matter of fact, if anything, they're going up. And that's because our equipment out there is overdutied. It's, the stuff that I worked on in 1979 was maybe 20 years old. The older stuff from 1959 was old. That was 20 years old. It's still there, and now it's 44 years older or 43 years older. So so it's overdutied, and if it's not maintained, it's going to fail. And you're getting more and more of those failures, so you're going to have that kind of thing. And some people think they'll put a shield on and they're good to go, and in reality they should have had a suit on because it's a much higher arc flash because the fault current is worse than it was. That's why it's required to be done every 5 years, so that when there's changes in fault current or changes in anything in the system, you're updating it to reasonable levels and not letting it get out of hand. So this just talks about you can work on stuff energized as long as you know if there's an increased or additional hazard or that's infeasible to shut it down, you can work on it live, provided you can do it safely. So there's stuff like this that will help you prevent an arc flash and prevent shock by covering that up, or at least reducing the likelihood of occurrence.
Lee, we have another question for this.
Yeah. Yes.
Don's asking, how do you assess the condition of maintenance? Any guidance there?
Yeah. So that's something that should be documented. So usually when people do maintenance, they'll have a sticker and they'll put a sticker on the equipment and they'll tell the date and the time that it was maintained and by whom. So if you have a contracted employer, and they'll come in and they'll put the sticker on there. Also, if you have your own internal maintenance program, sometimes there's a electronic program that you can follow, or sometimes people just use a spreadsheet based on NFPA 70B data. There's a lot of good information on how to start and how to maintain a good maintenance program in NFPA 70B, as well as a bunch of checklists that can be used for maintaining panels and breakers, transfer switches, bus ducts, motor control centers, transformers. So there's all kinds of checklists in there that are good. And that's one document you can still get electronically, I think. The NFPA 70 is only available in a book form, but I think electronically you can get 70B. But don't quote me on that. I have it electronically, but I think they're still doing it. Okay. So that's really where you go by the records and the stickers and things like that. So assessing the risk. So you take a look at these two switch gears, and one of them is 1964. They're both 1600 amp. They're both 2000 kVA transformers, and they're both 480 volts. So they're essentially identical hazards, you would think, right? So the first instinct, it would be for me and most people, is the 1964 switchgear is going to be a little scarier than the 2004 switchgear. On the other hand, though, let's take a look at this a little bit deeper. This one has a maintenance sticker, and it's got a pile of stickers on it. So it's got a sticker that says it's been maintained in the last year, and it's stuck on top of a bunch of other stickers. So it tells me this thing's been maintained pretty regularly, because it's been all these stickers. So that's one thing. I go to the 2004 sticker, which is now 18 years old, and there's no stickers. There's nothing on here at all. I asked the company about it. Do you have records? Nope, haven't done maintenance on it yet. 18 years old. Okay. Now that's starting to swing a little bit more in this direction as far as the safe work practices. Look into it a little bit further. I see that this transformer has got a 3.6% impedance on this transformer, and this one has a 5.5% impedance. So this is going to be probably 60,000 amps, and this is probably going to be 30,000 amps, somewhere in that range. So that's going to increase the available fault current. That available fault current is going to increase the arc flash level. So that's going to be where the feed comes into the main switch gear on either side, and that's going to have an impact. So now we're swinging back to the new switch gear again. But now I'm going to work down in this area in the main distribution panel. This one is an arm. It's a mechanical switch, and it's fused. So there's fuses down here protecting the main distribution panel. So the fuses are not required maintenance. They're going to operate the way they're supposed to. So I think down here, even though you have to gear up for the worst case in here, your likelihood of occurrence or having a high risk level arc flash is going to be pretty low, because your fuses are going to trip pretty quickly, and they're not maintained. They're not required to be maintained. So that's now turning it back into this range a little bit better. And if I'm going to be operating a switch in one of these switches, like so this one versus this one, or this one, we'll say this one right here versus this one, they're about the same position. I'm more comfortable operating this one than I will be on this one because this main, I don't know if it's going to trip the way it's supposed to, and that's going to be what's going to protect the line side of this switch. That's what doing an assessment's all about, just a risk assessment before your work. But that gives you an idea of some things to think about when you go.
Lee, we got a couple other questions in this area.
Yeah.
Would you recommend layering FR clothing, especially when you're switching?
I would recommend layering when it's required to be layered. So assess the hazard, know what the arc flash level is. If I have an arc flash level of, I have a label, the engineering study's been done, the label says 16.6 calories. I'm going to layer up to beyond 16.6. My personal system, I don't use a balaclava and a shield. I use only a hood. And my hood, I like it because it's got air supply and it's got a light on it. I can see very well, and it's quick on and off and easy on and off. And it keeps the steam out of the screen and the shield, and that works really well. And then I put on coveralls. If an engineering study's been done, you can layer up to the level that you have if possible. The coveralls I put over my arc-rated shirt and pants, if I add them together, comes to 23.3 calories per square centimeter, but tested as a system, it's 40.7. So I could put coveralls over my shirt and pants, and I'm already at 40.7. I'm the same as a suit. So I only have to carry coveralls, a shield, and a hood, and my rubber gloves, and I'm done. I'm good for anything. However, if I go to a place where an arc flash hazard has not been done, then I have to go through and use tables. And if you use tables, if it's over 8 calories, you have to wear a full suit. And so I would have to bring a full suit. If I'm doing data collection for a new client, I have to go in there with a full suit because I don't. You can only layer up if an engineering study's been done. So I hope that helps.
That was
So
good.
you,
Is,
one quick follow up. To do layering, you have to use the same manufacturer or test it as a system yourself. So generally that's going to cost you a lot of money plus a lot of clothing to get there. So you're better off to just make sure if you're using Bulwark, for example, use Bulwark for shirt and pants and coveralls. If you're using Tyndale, the same thing. Can't use Tyndale coveralls and Bulwark shirt and pants. So because they haven't been tested as a system.
so another question here, is there any electrical equipment that do not require arc flash analysis?
Generally, when you're downstream, the arc flash studies generally go down to the panel level. They can go further, and we've done that. Some companies say let's go through. We want everything labeled, lay all disconnects and everything. Sometimes we get to a point where we can generically label at very low levels, and just we color code our labels. So a green label would be generically low, less than 1.2 calories per square centimeter. But some companies just are okay with the panel, and whatever's feeding the low level panels would be low levels most of the time. Not that that's always that way, but often it is. But it's not. There's no requirement as to what needs to be done as long as you can assess the hazard based on your system that you have. So if your system is all the disconnects on the floor are 30 amp disconnects that are hazard category 0, fed by this low level panel, and you know that, and everybody that works knows that, that's okay. It would be good probably to have some label to say that it is low level to be sure. But sometimes you have controllers, sometimes control cabinets and things like that. They're usually pretty low level, usually, unless they're significant size cabinets fed by a 400 amp breaker. But generally they're pretty low. But some companies want them labeled as well, so it's up to the company.
Here's a timely one. Doug is asking the question, did the requirement for suiting up change? I thought it was using, or we used to use Cat 2 rated clothing for data
Yeah.
collection.
Oh, well, for data collection, if you're collecting data for your engineering study, you don't know what the arc flash level is, so you can make assumptions and do whatever you want, but main switchgear like these kinds of things, if you're going to open these up, you'd have to have a full suit to do that if you don't know what the analysis says. I mean, you're going to still look at fault current and clearing time and come up with the and I'm going to go through the tables. You're going to use the NFPA tables, but if you can't use the category 2 table because your available fault current is higher than what's on the table, then you got to beef it up, and that would be using a full suit.
Here's another question that's pretty interesting. Sometimes a client puts a study on hold because of the cost. What would be
Hmm.
considered cost effective and fair to complete an ARC study, and what factors should be considered in estimating the fee?
Yeah. So what I've done in the past, I've run into that quite a bit actually, is I will do it in stages. So this year we'll budget to do the utility and the main switchgear, and then next year we'll go to the panel level. And the following year we may go to the control panel and disconnect level, depending on what it is. So just in a tier system, but at least it kind of gives you a little bit of an idea on the highest level stuff what your PP needs to be. So, and then you'd use the tables for anything that you haven't done yet. So the panels, you just go by the tables, but you'll know from the original study of the main switchgear if your fault current is such that you can use the tables, and that's the key to getting it started. So that's an important way to go, and that seems to work pretty well. But some places where they have 50 buildings and it gets it can get very costly. In those places, I'll say, all right, let's take the single phase buildings and let's put generic labels on them. Boom, those 30 are done, and then work your way from there and maybe do the main switches, the main panels for each building, and then work your way down the following year. It helps them to budget.
And then Simon has one question before you go further.
Okay.
Do the pump starters require labels?
Uh, if it's expected that I mean, if I'm feeding anything with a breaker that's greater than 50 amps, I'll probably put a label on it. So it depends on what size pumps there are before I decide if I want to label it or not. But if I suspect that the arc flash level is going to be higher than zero, what would used to be called zero, if it's over 1.2, I would probably put a label on it. Okay, 335, just as this is the PPE requirements. So OSHA doesn't have anything for general industry and construction other than utility standards about PPE, arc flash PPE. So we go by this 335, 1910 335, and that's what OSHA uses to cite arc flash PPE because it's worded very generically and very brilliantly by David, um, oh, what's his name? The guy, the director, he was the director of OSHA that wrote this standard. So he's now retired, but so employees work in an area where there are electrical hazards shall be provided with and shall use protective equipment that is designed and constructed for the specific parts of the body to be protected and the work to be performed. So it doesn't say what parts of the body, it doesn't say what kind of work, and it doesn't say if it's shock or arc flash, it doesn't say anything. It's just electrical hazards. So they can cite a company for not providing arc flash PPE, and then of course they can go into the PPE standard for the requirements for doing an assessment to determine the PPE. Got to maintain the equipment in good shape. Make sure you train your employees, especially if they're working with chemicals or oil or they sweat a lot. It's hot area, that kind of thing. Those things will impact uh, the performance of your PPE. And make sure you test it. One thing I learned, I was doing an arc flash analysis. I was doing some data collection, and I put a hood on to go into a 208 transfer switch, a hood with my coveralls and so forth. And so I'm doing this arc, and I put the hood on, and a bug goes across the screen, and I go to brush it off, and it was actually on the inside. So I closed the door to the transfer switch, threw off my hard hat, and I didn't know if it was a brown recluse spider or what it was. And but anyways, I learned from that event that I need to inspect my hard hat every time before I use it, because I mean, not my hard hat, but my hood, because I may not use it for a year or two, and who knows what can crawl into this thing in that amount of time. So that's another thing to do, is visually inspect it. Okay.
Lee, we're getting short of time, but I wanted to fit this question in. And one looks like Muhammad is asking, what do you do if you can't get the short circuit current, three-phase or single-phase, from the utility company?
So that happens a lot too. So you use, infinite bus kind of data, which is not, it's problematic. It's not going to be as accurate as it should be. I have gone through a year before, and one time I contacted I wrote on the report, I wrote a draft report, and in the draft report I said this may be extremely high, or maybe higher than what we're saying, but it would be basically I'm saying it's the fault of the utility, blah blah blah. So I sent that to the legal team of the utility, and they hit the roof. You can't write that, blah blah. I said, of course I can, because it's true. And so they ended up pushing from their end to their engineering department, saying, you need to get this guy some information. So there's more than one way to skin a cat, as they say, but we were able to get it. It just took a long time. Sometimes it's difficult. So we'll use infinite bus data, but it's not. It can be actually worse by using that. It could be actually not as bad as what it really is. So we'll usually recommend going up one level higher than what we recommend. Okay, we're going to talk about tables and labels. I want to go through this stuff if I can here. So this is the table that you would use. So you look at what it is you're doing. So this is a 240 volt up to 600 volt panel, maximum of 25,000 amps, and 3 cycles of clearing time, 2 cycles of clearing time. So if either one of those are not true, if you're not within the 25,000 amps, or you have greater than 2 cycles, then you can't use this. That's the limitations of the labels, of the tables rather. If you are within that range, then you could go with category 2, and you have a 3-foot arc flash boundary. So you can use this if it's within the parameters. That's the problem with this. People are using this table and not following the parameters. And if you've got like the arc flash analysis I showed you was 76 calories. If you look on here, working on that switchgear with 35,000 amps, it's a category 4. Well, you can't wear a category 4 because it was 76 calories. And the reason why is because it exceeded 35,000 amps. And that's why you have to look at that level and make sure you follow those sections. Once you know the category rating of PPE, then you've got the 1, 2, 3, and 4. Tells you what it is you need to wear. And this works fine, but as long as you're within the ranges. So the categories are basically, these used to be category 0. They're not applicable anymore. The reason why this guy's got a hard hat and rubber gloves, of course, is the exposure to shock. Category 1 is 1.2 to 4. That's a shield. Category 2, 4 to 8. Category 3 and 4 is a suit. So once you're over 8, you're in a suit. That's if you've not done a study. That's another drawback of not doing an arc flash study, because once you do this, you're in a full suit after 8 calories, versus doing an engineering study and having 18.2 and layering up to whatever you need to layer up to, and not necessarily wearing a suit. So an engineering study, this is not a real good example of an engineering study, so I'll tell you why. But each one of these will represent a label, and it tells you what the arc flash boundary is and the calorie rating per square centimeter for your PPE level. So here's the problem. So this one, we've got 480 volts, main distribution panel with a generator. It's 329-inch arc flash boundary, 87 calories. That's what's going to be on the label. So you start looking into this a little further. You look at trip time, 81 seconds. So in reality, there's a the standards say, the 1584 standards say you can use the default 2-second trip time when you have these very long trip times. And so who is going to stand there for 81 seconds with a, it's not going to happen. So 2 seconds is enough time for you to get out of the way or get blown away. So this is not an accurate number for one thing. So this is what the label looks like. Then you can look at this MD1 with a generator, then MD1 without a generator. Whoops, and that's down here. So it's down to 35. So you can lock out the generator and be down below 40. That's still at 81 seconds. And then the generator only is now, that's got a reasonable clearing time, and it's 24 calories per square centimeter, so it's reasonable. The thing that's really quite bad about this is 3 different scenarios, and all of this will be impacted by these 3 different scenarios. So there should be 3 spreadsheets, total spreadsheets for all 3 scenarios. So whatever the scenario is, you can go into it and see where you're at. So that's another reason why you want to look at the studies and have access to the studies, so you can have this spreadsheet, because you're looking at a label and you say, well, I can't go in there, got to shut it down. And that's all you needed to do is open the door from a distance and do an infrared test. Well, can't do an infrared test, it's too hazardous. Well, you can, if you lock out the generator, you can do it. Or if the generator's running, you lock out the utility, you can do it. But that's looking at the table. So here's our colors. Our green color is generic low, and then the blue is generally, this is actually a low level, 18.3 inches, 1.1 calories. So it's just non-melting clothing, eye protection. And so if you go over here, once you get over 4, it goes to yellow. And this tells you the calorie rating, the distance, the PP requirements. I put some definitions for the approach boundaries so people remember what they are. I also put the fed by information so we know where to lock it out. And I also put the available fault current on the label. So that's one thing that NEC requires now. So I started doing this back in 2006, long before NEC required it. And then orange is over 8 and red is over 40. All right, so, and this is a layering chart with NFPA, with Tyndale, the company that I use for my clothing. So I'll put these two together, and I'm at 10.4 calories. 12.4 plus 10.9 equals 23.3, tested as a system at 40.7. This is a new 2021. The outer layer no longer needs to be fully arc flash rated. So this is FR rated and it's fine, but it's not giving me arc flash protection. It just won't flame up. So some factors to consider on failure. So some of the things are due to lack of maintenance, and including the lack of maintenance includes short circuit and ground and the coordination studies. Communications, human errors sometimes will cause the actual fault itself. It can be during maintenance, it can be other times, but a lot of times during maintenance. Sometimes static or other types of discharges, or fumes and dust and things like that. And sometimes people just aren't trained to know what's going on. Grounding is really important. So you have grounds like this that are very high resistance. It's going to have an impact on the time current curve of the breaker, because a breaker has to see the fault. It has to have reference to ground to see that fault. And if it doesn't, if it's got a high impedance fault, it's not going to trip the breaker as the way it should. It's going to take a lot more time, which then can cause more ionization and more likelihood of failure. So you want to have good grounding connections. So this is a grounding bus. This is a grounding bus, but it's a piece of channel. It's not really designed for electrical. But this is a good solid, low impedance grounding bus. We want less than 25 ohms of resistance on our grounding bus systems. Here's some things that cause arc flashes. So they missed the bushing. They forgot to put it on there. Now you got the wire skinned. So that's going to be an arc flash happening anytime. Same thing here is going to happen, right? So these wires are old, and there's bare metal that they can cut up against, and it's a matter of time. It's going to happen. Any kind of, where you have abrasion protection, you need abrasion protection for these things. Got to have a connector, and you can't use flexible wire for temporary wiring, for permanent wiring anyway. Infrared testing is a good thing. So this just says this was actually over torqued. So you have to torque your electrical connections to make sure they're proper. Over torquing is just as bad as under torquing. So you use a torque wrench or torque screwdrivers to do your electrical connections. They're required. Also now a new requirement is that manufacturers have to put the torque setting on the terminal itself, not just on the box of terminals. So this is the result of, if you don't pick it up with an infrared test and you let it go, then this ends up happening, and then of course you have an outage, maybe damages. This is the NEC requirements for tightening and torquing as your equipment. Things need to be UL listed. So this is a UL listed splice. There's the UL marking. These clamps, if you look at the UL listing of these clamps, there's nothing that says about electrical connection. They're hose clamps. So, of course, the next thing the guy's going to do after he's got his 3 clamps on there, he's going to put about 15 layers of black tape. Then he's going to have his splice done. This is going back to short circuit. So this is a 600 amp breaker that's rated for 35,000 amps in a 65,000 amp fault. So it's an old breaker. It was rated for the fault current at the time it was installed, but it's no longer rated. And it blows up, and it doesn't operate in the time current curve it's supposed to. Same thing here. It's a breaker that's rated for 10,000 amps and a 35,000 amp fault. The other places where arc flashes occur, bad cables. So if you see stuff like this, these are generator cables, lock it out. Make sure it's shut down until it's fixed. Other things that can be a problem that can have an impact on arc flash is corrosive atmospheres and damage from dust and fumes and things like that. Not properly testing transformers and having oil fail. So transformer oil needs to be tested to make sure the oxygen level is proper and there's no carbon buildup and so forth. Loose connections can cause arc flashes. Sometimes interlocks, failed interlocks, cause them to close in a grounding switch on an energized bus without thinking. Faulty switches that should have been locked out but weren't, so that happens sometimes. So let's talk a little bit about due diligence. How are we doing on our time here? We're doing okay. So we want to take every precaution reasonable in the circumstance to protect the worker. That's what due diligence is all about. Every precaution reasonable. Doesn't mean every precaution, but we have to do our best to make sure it works. To secure workers from risk to their safety and health and welfare arising out of or in connection with activity in their workspace. So it's a foundation of successful safety program. It's just part of the foundation. So there's a whole hierarchy of things to do, but this is a big part of it. It's an investment in accident prevention and reduce accident costs, proactive tool. It presents, and I'm not going to go too much into detail on this, but it's present in the workplace before an accident happens to prevent the accident from happening. It includes hazard analysis to determine written policies, procedures, and practices. So that's due diligence. Without an effective electrical maintenance program, including doing that short circuit and coordination study, management assumes greatly increased risk of serious electrical failure and its consequences. So maintenance is a big deal, and a lot of companies are just not doing it, and equipment is getting older and older and older, and that's why we're having more arc flash incidences occur out there. Electrical maintenance program is a form of protection against accidents, lost production, loss of profit. An effective program. This is language out of the NFPA 70B. So it satisfies an important part of management's responsibility for keeping costs down and production up, and that's a big deal. So a lot of companies will say, "Geez, we're going to have to hire another person to do this maintenance to get this done." Well, the cost of that other person is probably going to triple or quadruple in other ways of keeping production up. Because you have one outage, if you just think about production time, it could be critical. So the negligence in a tort case, so first off, we have a duty to prevent foreseeable harm. So we know that arc flashes can hurt people, so we've got a duty to fix that. The breach of duty results from acting irresponsibly under the circumstances that breach legal duty to care. So if you decide you're just not going to do it because it's too costly, that's the breach of the duty to care. And then damage and losses caused from harm as a result of the breach of duty, and then that's where the tort case comes into play. So why are we not doing arc flash analysis? It costs money. It's fairly expensive. It could consume productive time and may cause shutdown time. If we have a switchgear that we know, we do enough of a study to know what the fault current is, so we can go into the switchgear or not go into it. If we can't go into it because the fault current is too high or the clearing time is not low enough, then we have to schedule a shutdown with that company. And so usually that's a midnight on a Saturday night or some crazy thing. But they usually will do it for us if they want to get this study done. But sometimes that happens. Here's a few case studies. So lack of breaker maintenance escalates a destructive arc fault and this was an overdutied breaker that would have been picked up in an arc flash study by doing the short circuit study. So it leaves an office high-rise building in a major fire. So this is a high-rise building that had a vertical bus duct, had a main switch on the bottom, and then every floor had panels. And it failed, and it just blew this thing right up, and it ended up, one maintenance work was fatally injured. So it's $32 million. You can do a lot of maintenance for that kind of money. Here's one that was $13.9 million. Then they saw them in favor of the plaintiff for lack of maintenance again. $800,000 for not maintaining a switch. And these are all different arc flash and burn fatality. Some were fatalities, not all fatalities, but some were loss of business. So they ended up in the millions, civil litigation. This one was a generator that was set up. So this is a 2 megawatt generator. The guy had to go in the side to do some work. It's fed from a 2500 kVA transformer, and so that's fed from a pole, and it's going right through the load side of the breaker. He didn't realize that this was live, so he shut down the breaker, shut down the e-stop on the generator, started doing some work, and got shocked on 277 volts on the feed coming from here. So he survived it, and he ended up after the shock sitting on the stairs, not knowing how he got there, and he was talking to a supervisor, didn't remember calling the supervisor, and the supervisor called 911 and got him going and all that. So I started looking at this, and I said, well, what happened if you had a screwdriver that crossed against this? What would the arc flash level be with this transformer? So we got the transformer nameplate data, and we came up with this chart. So 75% of the full fault current is 45,000 amps. So I use that just as a tool. So at 18 inches, it's 101 calories. That's where he was setting. Now, he was working with cotton clothing on. He would have just been nothing but toast. And I asked our engineer to give me what it is at 3 feet as well, and it's 36. So that when you want to test, verify, de-energized, there's a little cover on the back, and you can do that and maintain 3 feet by using a 3-foot stick to test. So that's all good. But what would happen if that really actually happened? This is a 3516 generator. It's the same generator as what you just saw. 2 megawatt generator. You can see all the molten metal is gone. That would have happened right in front of his face. And then to see what the suit that occurred, if he was wearing a 40 calorie suit, that's what it looks like in that kind of an arc flash. Now the person that was wearing this suit was in the hospital for 1 week and released. So that suit did its job, did what it needed to do. But it's a pretty serious arc flash, and people just need to realize that. Now, what can we do differently here? I tell the cat dealers, because this happens a lot with the utilities, they all over the place, and I work a lot with cat dealers around the country. But I said, bring in a fuse disconnect on a sked or a pallet or however you want to rent it, and just set it up so that there's a fuse disconnect here, so they have a lockout tagout point that they can use. Plus, it's going to bring down the arc flash level significantly by having it fused disconnect. So a lot of them are doing that now. This is new in 2021. So this is what they're saying. If you have something greater than 40 calories and you shut it down and lock it out, you still have to verify it's off. So you'll use a distance, test it at a distance. I've been practicing this for at least 10 or 15 years, and encouraging this kind of a test. So this is done in addition to a dead live contact test, face to ground, face to face test. So you'll do this first, check it at a known source, verify de-energize, go back to the known source, and then when that all tests good, go up with your contact tester and test face to ground and face to face readings. Do that dead live as well. So that's an additional step. Mitigating the arc flash hazards. Distance, again, is your friend. So remote racking, remote switching is a good thing. Now they're making remote racking, remote switching wireless, which is even better. Normally you wouldn't stand in front, you'd stand off to the side, but this for the photo, it just give you an idea what you're working with. This guy actually routed out a piece of plastic and put it on a handle. He's got a string and he's way over here. And that's pretty ingenious. This is a great tool. It's an arc flash relay. So the fiber optics will run all through the switchgear, and then there's contacts, and so this might be connected to two separate breakers. One might be a main breaker here, another one might be a tie breaker on this side. And so it's going to go to the shunt trip of these breakers, and it'll trip it so fast that it brings the arc flash way down. And it doesn't mess up coordination, which is the real beauty of this. It just really makes the trip time a lot faster and doesn't screw up anything else. Maintenance breaker settings. Sometimes if you have a maintenance setting, you can put the breaker down here on a lower trips time to bring down your arc flash level while you're doing maintenance and racking out breakers and stuff. The problem with that is now that's going to be what's much more sensitive than breakers downstream. It's not coordinated anymore. So you could have a blow dryer in the bathroom cause the whole plant to go down, and you don't want that to happen. So it's a little risky. Arc flash relays, arc flash switchgear, arc rated switchgear. This is very expensive, but you notice how this is real heavy steel, bolted, real close in bolts. So this stuff can handle the fault, the actual arc flash itself. A lot of times what they'll do is they'll set this up so that this is now going outside the building somewhere in a fenced-in area, kind of coming downward toward the ground, and kind of that's the way it goes. The problem then is you got to make sure and keep people away. There was one company that wanted to do some maintenance on the fence that was around the arc rated area. They said, "Is that okay?" And I said, "Well, not really." I said, because if that has an arc flash inside, you're going to do the same thing as you would if you had non-arc rated stuff inside without having PPE. So I said, if it depends what it is, but maybe you want to put people in a suit to do it, or maybe you want to shut down and do it on a shutdown to make sure that they can do it. So it depends. You're just shifting the hazard to another place that may be safer, but you got to still consider you got a hazard there that you still have to deal with. All right. Let's see how we're doing on time. Oh, we're doing all right.
I think we've overrun our time slot.
Oh, we have. Oh, I'm sorry. I thought I had till 2:30. I'm so sorry about that. We still have people on board?
Oh yeah. Let's go
Okay,
to
good.
contact information.
Yeah, let's just go with that. So we just covered this is the objectives that we talked about. So hopefully we covered that. And so this is the my website and well, it is my website as well, but it's my email, Lee at workplacesafetysolutions.com, and my number 802-288-9441 is my business number. If you do have questions, feel free to call or email me anytime. I appreciate that. And thanks for your time.
Lee, thank you for a good job. And any questions that we weren't able to get to during the broadcast, he will follow up via email. Thank you.
Absolutely.
Have a good day.
Thank you.